Well, good afternoon, ladies and gentlemen. It's with great pleasure that I was invited to introduce this afternoon's lecture. I'm Professor Richard Evershed from the University of Bristol. I'm a biogeochemist whose interests overlap somewhat peripherally with Professor Mark Maslin, who's going to be talking to you. I just have to mention a few formalities. Could you all make sure your mobile phones are switched off? Thank you very much. The lecture will be about 40 minutes. There'll be time for some questions at the end. I thought I'd start by just saying a few words about the Royal Society, who are organisers of this particular lecture and one or two other lectures in this festival. And I thought I'd just say a few words, because sometimes I think people don't quite appreciate the significance of the Royal Society as an organisation. It is the most prominent scientific society of the British Isles. And it's an organisation that is a self-governing fellowship of some of the most distinguished scientists in the British Isles, and we also have very distinguished foreign members as well. And the fundamental purpose of the Society is truly promoting excellence in science. And it serves, the Society performs a number of functions, as well as being a scholarly society which actually funds science, fundamental science. It also supports a large number of lectures and other events such as this. It also performs an extremely important function in providing what I would describe as a sort of rational advice to government on some of the most critical scientific matters of the day. So it's a very important organisation. But the purpose of this event is one very much the one which is right at the heart of the Royal Society as well, and that is to promote the wider interest in science, public interest in science. And I would strongly recommend, for those of you that haven't done so, that you go to the Royal Society website and look at all the events that the Royal Society takes part in, and you can even view some of the past lectures on royalsociety.tv. So I'd strongly recommend you do that. Anyway, that's enough about the Royal Society. Now let me say a few words about our speaker, Professor Mark Maslin. I've known Mark for quite a few years. He's Professor of Paleoclimatology, and he's from the University College London. I know Mark from his scholarly activities, but I didn't realise quite what an entrepreneur he was when I started to read a little bit more about him. He's co-founder and director of Carbon Associates Limited, is science advisor to the Global Cool Foundation, Global Precious Commodities PLC, and Carbon Sense Limited. But actually, most importantly, Mark is a member of the Cheltenham Science Festival Advisory Committee, which is by far his most important role. His areas of scientific expertise include the causes of past and future global climate change, and he has a particular interest, which we're going to hear a lot more about, in early human evolution. He's published more than 100 papers. He's written 7 popular books, and he is a Royal Society Wolfson Research Merit Scholar for his work on early human evolution, and he's just been awarded a 4-year Royal Society Industrial Fellowship. He's just returned from a workshop on theories of human evolution held at the Turkana Basin Institute in northern Kenya, which is hosted by the very famous paleoanthropologist Richard Leakey. We're going to hear a lot about his research on human evolution, but if you want to read more about it, he's just had a very nice article published in this Times magazine, Eureka, so I would strongly recommend that you take a look at that. Anyway, without further ado, it gives me great pleasure to welcome Mark to present his lecture, The Evolution of the Human Brain. Mark, take it away.
My friends. Right, I have to say, after an introduction like that, unfortunately, you know it's going to be all downhill. First thing, these are my friends. I'm a geek, so I don't get out much, so these are my friends, and I will be introducing them through the talk. What I want to try and do is tell you about human evolution, just give you in about 45 minutes some of the exciting new advances we're making and also why I'm so passionate about this subject. So I can't do it alone. I have friends and colleagues from Oxford, from Potsdam University, from New York, and from Berkeley, all of whom have actually contributed to this. And you also see there is a helicopter. We'll come back to the helicopter later. Right. So our earliest ancestor, we think, was sort of like a gorilla type that occurred about 6 to 7 million years ago in Chad. And we think that because of the gorilla-like features, we had this sort of adaptation to forest. However, this is where the fossils were found. So we already know that there have been profound changes in African climate over the last 6 to 7 million years. And that, for me, is where the story starts. How has this climate change influenced us and allows you to understand speech and have that huge brain that allows you to watch Coronation Street? I will come back to Coronation Street. So bipedalism came first, and I'm sorry, I have to do this joke. Lucy is not my ex-girlfriend. And I did have a girlfriend called Lucy. I promise you I did. And again, this was a revolution when this was found by Don Johansson because it showed that we started to walk upright first. So our ability to do this on stage and walk, and as supermodels do, okay, that was because of our locking knee. And these are the first ape. And Lucy comes up to here on my hip. And this is Lucy. Small-brained, slightly bigger than a chimpanzee, and it is, I'm really sorry, even though I have these in my office, it is very tempting, occasionally to, okay, you're very welcome to play with these later and do the same, okay? So, this is Lucy, and so the first question is, why? Why did we start to walk upright? Why was that more exciting than actually using your fists as chimpanzees along the ground? Now, the key thing is about East Africa is it's tectonically really, really fun because everything changes. And we know that the Rift Valley starts about 20 million years up in Ethiopia, and we start to have that doming, and we have this splitting. And the way I describe it in the Eureka magazine is it's a bit like your apple pie. It rises in the middle, and unfortunately, if you cook it a bit too much, it cuts in the middle and you have a crack. And that literally is the Rift Valley. And so if we have a look, this is central Kenya, and you can see these huge grabens that have actually been forced up. And even in the inner rift, this is a huge thrust and uplift. And just to give you some scale, that's our Jeep. Okay? So very tectonic active, and I would say that almost everything has changed in East Africa. And so what happens is about 20 million years ago, we have a hot spot underneath East Africa, and you get that sort of doming, that heating up and pushing up. This starts the apple pie effect, and you start getting some cracking, and that's where you start to get the Rift Valley forming. And then much later, it forms a big plateau. And this is something I stress a lot. It's called a valley, but it's hanging 1,000 feet up to 2,000 feet above sea level. So it's not a valley, really. It's hanging between two major mountain ranges. And what effect it has is the moisture in East Africa comes from the Congo and comes from the Indian Ocean. But when you start to build these huge mountain ranges, what happens is the rain gets concentrated in rain shadows on either side. And then finally, you start to actually block the rain from getting into the Rift Valley. So the Rift Valley then starts to dry out. The other thing I've put on the right-hand side is the Findlater Jet. You find that you have a mountain range nearly 1.5 miles high, which then acts like a racing track. The wind comes along off the Indian Ocean, hits that, spins round, and spins off and takes all that moisture off to India and the monsoonal system. So the effects on vegetation are quite clear. So you have nice wooded Africa, and then unfortunately we have some savanna, and then much more open territory. So the idea, the savanna hypothesis, is that our ancestors, the chimpanzee, which we split from about 6 to 7 million years ago, quite happy in the forest, quite happy surviving in the forest. And then our bipedal ancestor, like Arthropithecus ramidus, about 4.5 million years ago, found that this open landscape, this fragmented landscape, meant that being able to move distances efficiently was actually a good evolutionary trait. And this is something that I point out to my students, even the ones with a hangover, which is you can walk all day. You can travel a huge amount of distance bipedally. And if you imagine trying to do it on your knuckles, etc., it's incredibly tiring. So this is an efficient locomotion for an ape to actually travel large distances. And so people think that actually that ability to move around between different food sources was absolutely essential as the vegetation in East Africa started to fragment. But the thing that I'm really, really interested in is big brains. So the key thing is, firstly, walking upright came first, and then we got bigger brains. And you can see that from about 5 million years ago to about 2.5 million years ago, if you measure the brain capacity, it stays very similar. And it's only slightly more than a chimpanzee. Okay, so we haven't really got particularly smart. And then there's this huge jump, about 1.8 million years ago, there's a jump. And we jump to this, which is Homo erectus. And this, I once described him, if he was walking down the street in a three-piece suit, you'd go, rugby player. Okay? You wouldn't say, that's an alien species. And so, very much by that period of time, we have something that hasn't quite got our brain size, but really does look, apart from the very heavy brow ridges, hence the rugby player joke. And then the next jump comes about 1 million years ago, and we jump up to a bigger brain. And what's interesting is that this is slightly split from the species, because Homo habilis, the first Homo, occurs here, and is actually quite a small increase. And this is Homo habilis. And according to the experts, okay, this one is bigger than this one. Right. Well, again, the interesting thing is it's when things were discovered. Because this one was discovered by Louis Leakey with stone tools, this was the great leap forward. And so this was made a prominent new species. It's Homo. This is the ancestry of man. The interesting thing is, had we found Homo erectus first, that's clearly. So there's a bit of politics, particularly in anthropology. Richard Leakey, when I heard him talk, he unfortunately lost his legs when he was flying. People believe that his aeroplane was sabotaged when he was running the Kenyan Wildlife Service. And he steps up on the stage, and he's incredibly charismatic. And he hits his legs, so everybody knows they're false. And he goes, do you know what? It's great to be back in paleoanthropology, but I still think it's more dangerous than Kenyan politics. So hence why a lot of the paleoanthropologists don't like me, because I'm just a climatologist. What do I know about human evolution? Right. So for many years, from about the mid-1990s, the aridity hypothesis dominated the whole idea of human evolution. And so the idea that Peter Dominical in Lamont in Columbia University came up with, he said, look, here we have, from 4 million years, global climate cooling down. We have the big ice ages coming in, and we know from isotopes that actually it's getting more grassland in East Africa. And then he said, and actually, this is the dust record. This is the dust. So this is the dust blowing off Africa that you can see. This is the Sahara. This is the huge dust plume. And you can find that in ocean cores. And he said, look, here's the dust record, and actually you can see that there are steps in that data. I have to say, I've tried with a few pints of alcohol. I can't see it. And I have to say, friends of mine, Martin, have done some stats on it. And this whole myth of steps in aridity is a myth. It doesn't exist. They aren't there. So this wonderful paper in Science in 1995 just doesn't have what it says it has. So Martin and I started this in 2003. And I have to explain that we were stuck in a conference on the Amazon in Tucson, Arizona. Okay? Don't worry, that's what scientists do. They go to very odd places to talk about other odd places. And he basically was sitting in a talk, and I have to say, some of my colleagues, as I'm sure you're aware, aren't particularly good speakers. And so we were a bit dull. And so we were writing notes to each other, like naughty schoolboys, like the people at the back there. We were writing naughty, do you want to do work in Africa? Yes, I do. That'll be great, fantastic. And hence, the whole of this study came from naughty schoolboys writing notes. But we decided, actually, the ocean cores don't tell you what's happening in the Rift Valley. And that's where all the fossils are, and that's where we evolved. So why don't we go there and find out what's happening? And so this is exactly what we've done. We've done about 5 field seasons in the Rift Valley. And I have to say, you have to fly up there. And the helicopter. Helicopter is just a glorified taxi. Okay? It takes exactly 6 days, after which you stop taking photos of it. But again, it's incredible for field work. Because what usually happens is you get in your 4x4, you drive for 2.5 hours to the actual site, you get out, it's midday already, the heat has already started to hit upper 30s, lower 40s, you do an hour or two, you get back in your 4x4. Helicopter's fantastic. You can be on site just after dawn. So as soon as dawn comes up, you fly, you're on the site at 7 o'clock in the morning. You suddenly realize after 2 hours of working here, this is a rubbish site. So you call up the helicopter and move to the next one. So incredibly practical way of doing field work in the 21st century. But what I want to show you is this is the Suguta Valley in northern Kenya, and this is a wave-cut platform. And so what we've done is we've gone and found lots of lake sediments and seen where they are in relation to the rest of the actual environment and measured shorelines. And it gives us an incredible, powerful tool. So these are all the lake basins from Lake Malawi all the way up to Afar that we've been working on. And this is a blow-up of sort of the current lakes in Kenya, from Naivasha, from Baringo, all the way up to Lake Turkana, where it was a couple of weeks ago. And you have these beautiful, beautiful sort of sediments. So this is Karianduzi. So this is white sediment. It looks like the White Cliffs of Dover. And actually, it's made up of silica diatoms, which are small, single-celled organisms that use silica to build their shells instead of calcium carbonate. But they're incredibly informative, because each species tells you how fresh the lake was and how deep it was, because they all have a particular preference. So this is dated about 1 million years ago. And so we have at least 3 lakes that all occur at the same time. Then this is Lake Gashuru, dated about 1.7 million years. This is Martin, looking very cool, and that's one of my PhD students. And they mine this stuff in Kenya. I'm not going to ask this audience, but many of you may have soft drinks. Many of you may drink Coca-Cola. I'm not sure I'm allowed to mention that. You won't realize that it is filtered for all its impurities. Honestly, they have impurities. And it's actually this stuff. So there's a whole mining going on, as you can see in the background, of this diatomite, which is then heated up and then used as a fantastic filter for soft drinks. They are a lovely side issue, nothing to do with human evolution. Right, and you can see here, these lakes occur about 2 million years ago. And then this is Baringo, where we have a set of 5 lakes on top of each other with soils in between, showing how the climate's varied. And we have 2 at about 2.5 million years. So we came to this problem. So these are all the basins. So this is the south. This is Olduvai, all the way up to Afar in Ethiopia. And so we suddenly found that these lakes all occur at about the same time, and when species of early humans were changing. And so we suddenly realized that we had these lakes when Peter said that it was dry. It's like, ooh, how do we do this without getting ourselves into real trouble? And so you can see we can put all these lakes together, and so what I've done is just compress that all into when do lakes occur in East Africa. And you can see they're beautifully cyclic, 4.5, 4, 3.5, 3, 2.5, 2, 1, etc., through this period of time. And I'm just going to pick this period of time here for you to focus on. almost all the lake basins in East Africa are full of fresh water at this point in time. And we can do species diversity. So these are how many species of hominids. So how many of these guys were running around together in East Africa at the same time. And there is a point here, about 2 million years ago, that we have about 6 different species that we know of hominids running around. And so you can put this all together and start looking. So we have low levels of brain here, and then we have this massive brain expansion here, massive speciation, and huge amounts of lakes occurring in East Africa. And I've also put these lines on. These lines are when hominids actually left Africa. This one is when we went into South Africa, and these are when we actually went into Europe and Eurasia. And it means that the migration patterns of hominids also are driven by these lake occurrences. So when the actual basin fills up, it's actually no space for hominids, and they get pushed to the south and pushed to the north. So, did human evolution occur in the Garden of Eden? Were we surrounded, drinking cocktails around beautiful fresh lakes? No. The story is a little bit more interesting than that. And actually, it's because both Peter and we are both right. So these lakes actually are ephemeral. They actually occur in sets of 4 or 5. And these lakes come and go. They're not permanent features of the landscape, which actually is the key to understanding why our brains are so large. And this is because of the wobble. Okay? The Earth actually wobbles, unfortunately, on its axis. Now, we've known about this for many years, and we understand that this is how the big ice ages wax and wane on long timescales. But what we hadn't appreciated is the wobble called precession, which actually affects the seasons, has a huge effect in the tropics. So the way to understand precession is if you have a spinning top, as we all did as kids, you spin it and you let it go. And it spins round and round and round. But what you also notice is the axis, the plunger you've actually pushed, also wobbles round, but much slower. And in the case of the Earth goes around once every day, and actually this precession of the axis wobbles round a whole circuit once every 20,000 years. But what it does is it changes where the seasons are. So at the present, December is actually closest to the sun, but actually remember it's the tilt of the Earth that causes the seasons. Go back 5,000 years ago, September's closest, and then 11,000 years, June is. And what we found was that you can track these back. And this is where you actually talk to the physicists and the solar physicists, because they do all the wonderful gravitational calculations to work out the wobbles. And these wobbles go back in time, 8 million years plus, and actually has a huge effect on the amount of sunlight. So the top curve is insolation for the 21st of March on the equator. The way I sum this up is, say I have a student that's really, really annoying, okay? I give them a lux meter that basically measures sunlight, stick them at the equator, and send them in a time machine back every single day, back 8 million years. And what they record is the amount of sunlight is that curve there. And it shows you have a huge variation in the amount of seasonal sunlight you get at the equator. And you can put this into models to actually work out what effect it has. And this one shows you, if you have an ice age compared with a modern, you shift the rainfall patterns between the hemispheres. If you do this with precession modern and precession in the past, you do exactly the same. So just that little wobble and that change in seasonality in the tropics has the same effect on rainfall as actually having an ice age. So this is a very powerful tool to actually change rainfall in East Africa. So it seems that precession, this 20,000-year heartbeat of tropical climate, can change from Eden to hell very, very quickly. And for me, the excitement was now we actually have an understanding of these lakes and this changeable environment. How did this actually occur? And one other piece of evidence that we've been doing is we've been looking at Lake Seguta. And so this is Lake Legipes up there. It's a rather smelly alkaline lake, which is about 3-4 meters deep. but we know that only 9,000 years ago, and that's in our interglacial, not in the last ice age, but in the last interglacial, the whole of this area was full of fresh water, 300 meters deep of water. So this is Lake Seguta as it is now. This is hyper-arid. These are sand dunes. I apologize. These lines here, I couldn't work out what they were. Firstly, I had these visions of giant snakes. However, it turns out that the rich boys and girls from Nairobi fly up in their helicopters, get dropped off from a hovering, and they sand surf down these. So I should have just airbrushed them out, shouldn't I? Right. So we've done the paleo shorelines for about 7,000 to 8,000 years ago. And that is where the lake was on that mountain range. So the whole of this valley was actually full of fresh water. So we have this incredible environment that allows huge fluctuations in fresh water. And what we did then was saying, well, hang on, how does this actually work? How would this drive human evolution? And there's so many different views on how evolution works. And so we said, hang on, is it because you have the actual lakes appearing and it's that high energy? You have lots of resources, allows hominids to compete with each other and with different organisms. Is that the cause? And then there's this Peter's view, which is it's the high stress dry periods. And this is where another bit of the story comes in. Some of you may be wondering why I've left him all alone. Right, as you can see, he's not very smart. Okay, his brain is actually smaller than the Australopithecus. Now, the interesting thing is, look at that jaw. Okay, so at about 1.8 million years, this also evolves. So there seems to be two different strategies going. Eat anything, think your way out of trouble. Okay? So there's two different strategies going on. And so people have suggested perhaps it's... I didn't mean to insult you. Right. It always goes wrong with me. So here we have dry periods. So is it the dry periods driving this species to actually get that bigger draw so they can use the tubers and dig up any food they have? And then there's Rick Potts that suggested it's this variability, extreme variability, that actually means that you have to plan the future. You have to actually try and understand how to adapt to a rapid changing environment. My PhD student, Kathy Wilson, has done some brilliant work on the lakes. And what she's found is, by looking at the lake sediments, the lakes appear incredibly rapidly. They literally just appear in the geological record. Bang. And we think that we're talking about less than 100 years for that valley to go from being dry to being full of a freshwater lake. And this actually makes the evolutionists happy, because actually, yes, evolution works on the individuals. Do you survive? But to actually pass on a trait, you need a couple of generations of stress to be able to pass this on. She also sees that actually getting rid of the lake actually is very jagged, and actually the lake shrinks, expands, and then finally, death knell, it disappears. And so we now have some real feel for the timing and how much timing these lakes would have occurred. So it means that early human evolution occurred in an environment with climate change on the human timescale. And so we can really start to put that together. So I'm going to try and conclude, and I'll try and put some flesh on the skulls. First thing is the tectonics in East Africa is incredibly important because everything changes. You go from flat tropical rainforest to random bits of savanna, mountain forest, rainforest, the whole works. You find everything in that environment. The other thing the tectonics does is it produces these basins, these isolated basins, which Martin's called amplifier basins. It's because any change in the rainfall, slightly up or down, is amplified by these basins, allowing them to fill up or empty very quickly, producing this stress of lakes coming and going. And these lakes, we think, we can show are linked to speciation, so the diversity of our ancestors. We can link them to brain expansion, particularly at 1.8 million years when Homo erectus appears on the scene. That seems to occur when almost all the Rift Valley was actually having huge lakes, then disappearing. Huge lakes, and then disappearing. The lakes appear in less than 100 years, and I think that is a huge step forward in our understanding. Instead of just arm waving and going, oh look, climate changes, it might have affected us, we can have a real feel that actual climate was changing on a timescale that would influence whether you actually survived and whether your children survived the next year or the next decade. Lakes disappearing, highly variable. And again, I think it's interesting that there are two, as I said, two ways out. You either eat your way out or you think your way out. And I think the most important thing is that this thinking your way out is actually linked to our survival. And Robin Dunbar, who will be talking later this week, and I do encourage you to go to his talks because he is absolutely fantastic. He argues, and this is why I'm going to come back to Coronation Street, is that it's the social brain. It's the ability for us to work in teams, to be able to provide food for others who have knowledge but may not be able to actually participate in food gathering. That ability to accumulate culture and knowledge, to be able to ask questions such as, hang on, when the lake last disappeared, where did we go and get food? And that ability to adapt to the environment. And for me, that's incredibly important. That ability to adapt is hardwired into us. If you don't believe me, I'll dig it out of my pocket. 30-odd years ago, we had no idea what this is, okay? But my children can do things on this that I can't, okay? And so the adaptability of our species and the ability to be a social organism, even by telephone, Facebook, and things like that, has actually shown our ability to change. And I'm going to leave this with my photograph of my sunsets, my beautiful sunsets, my love of Kenya and East Africa, and to leave you with the thought that if we were truly born out of climate change and our ability to deal with natural climate change and think our way out, isn't it true that we are smart enough to actually be able to deal with our own generated climate change in the future? Thank you very much.
Okay, Mark, that's great. Thank you very much. So I'm supposed to add a sense of organisation to this by sort of coordinating questions. So I'm sure there are plenty of questions. So, gentleman here with the glasses. Yeah, microphones will come round, so just wait until they appear.
You talk as if it all took place in the Rift Valley. Is that true, or was there also stress in other places in Africa? Because I was reading Chris Stringer's book, and he gives the impression that there were sort of clumps of humans fleeing all over the four corners of Africa, looking for, I think he calls them refugia. Mm-hmm. One had the impression that there was a lot of winnowing out that went out, extinctions and so on, and variability outside the Rift Valley. Is that true?
Right, that's a fantastic question. The first thing is to say, I might have been a bit mean about Australopithecus africanus. You're absolutely right. This creature was all the way in Africa. So it was in North Africa and it was in South Africa. And so it was continental-wide and actually very successful. What we think we found is that new species, so the new species, when they appear, they only seem to appear in East Africa. You then find them later in South Africa. We think that's their migration. You find them in North Africa, and then later on when you get Homo erectus, you find them in Dmanisi in southern Russia and all the way through to Indonesia. And so what we think, and of course we're always beholden on the fossil finds, and there's always surprises out there, is we think that the new species actually appear in East Africa and then actually are leaving either out of the Rift Valley and then actually from about 1.5 0.8 million years onwards actually even leave Africa. So I hope that answers your question.
Anybody else? Please call out if
one over
you're
there.
behind a pillar.
Yeah. Yeah, this is why it's called the pillar room.
Oh,
Yeah.
no, of course.
Hi. If this variability in climate gave us bigger jaws and bigger brains, what does the future projected variability in climate, droughts and floods, going to do to us?
Right. That's the future of evolution. Now, again, I have to tell you, you should go and see Mark Thomas, who is a colleague of mine at UCL, who's also talking, who's a geneticist, who does actually talk about future evolution. We are continuing to evolve. Okay? The interesting thing is some of the fantastic stuff coming out of genetics now and ancient DNA show that light skin only occurred 15,000 years ago. Lactose tolerance, the ability to actually have the enzyme to process milk, which I know that Richard's also worked on, is only about 7,000 years old. So our bodies and our species is still starting to evolve. The interesting thing, though, the idea you're actually going to get a new species suddenly appearing, unfortunately, we are a huge weed. We cover every single continent except Antarctica, and there are 7 billion of us. So actually producing an evolutionary pulse that changes our physical form in a huge way is unlikely. But you do get lots of small micro changes that are occurring all the time.
Would it be true to say that the future drivers on our evolution are probably going to become more social than perhaps environmental, which is what you were saying?
No,
here,
I think that they will be environmental, but I think there will be much more things like how do our bodies adapt to antibiotics? How do we adapt to more resilient strains of malaria? How do we actually deal with certain diseases? So I think there's lots of adaptation that's going to occur and then passed on.
Okay. Anybody else?
Some there? Oh.
Did fire, the control of fire and the control of cooking, have much of an influence on our brain size?
Right. This fire is a tricky question. Not because we don't want to know, but it's very difficult to find in the record and actually prove it's not a natural fire. So, the last, and this was 2 weeks ago, the last paper we saw that we actually trust the data, that looks very good, puts fire at occurring 1.4 million years ago. So, after Homo erectus, but somewhere in that brain expansion period. And so we think that is when we had the first evidence. The problem is that absence of evidence before that doesn't mean fire wasn't there. What people have said is important is meat eating through this period, and particularly with Homo erectus, is incredibly important. So it doesn't matter if it's raw meat, the high energy cost. Because as colleagues of mine point out, having this big brain is actually a real downer. Firstly, actually, infant and mother mortality rates in humans are much higher than other mammals, okay? Because it's a really stupid system. You're trying to get this huge concrete melon, as my wife pointed out, to come out. And then you have this completely helpless infant for 3 years before it can actually survive. So meat eating, and the huge, by the way, 20% of all your calories just goes on that brain, which is hardwired into understanding soap operas, okay? But it's true. If you think about it, most of the time, and this is very true of scientists, you do a lot of gossiping. You don't know you do, but you do. Okay? And so most of our time is about social interactions. It's how we actually navigate our way through the world is actually understanding people's facial expressions and how people then talk to each other. And Robin Dunbar says actually the reason for the huge brain is that sort of interaction. So if Richard and I are talking here, and pretend you're not here, okay? We're talking, and we suddenly start talking about a colleague of ours. Now, I have to work out, does Richard like this colleague or doesn't he? You know, and so like, yeah, what do you think about John? Oh, John's okay, yeah, fine, yeah. Yeah, but he dissed my paper. Oh, right, okay. And then we can also go further. We can actually talk about John and his relationship with the woman over there. Okay, so we can now start talking, and we can go to 5 levels. If you ever look at a Shakespeare play, the amount of duplicity, we're really good at this, by the way, duplicity, goes very, very deep. About 5 different levels that you can actually con people, okay? We're very good at that. And that's actually what Robin says is why we have that big brain. Building those social groups and working as teams takes a lot of brain power.
Gentleman here with a beard.
When you say the lakes declined in 100 years, you're suggesting that the population crashed and essentially got very high variability coming forward? Or what did the evolutionary impetus come from the uncertainty in the lakes at a later date?
Right. I think, and this is only my opinion, firstly, the lakes appear in 100 years. And actually, the variability is about on the same scale, but they do this when they go. For me, it's about resources. It's actually whether the resources suddenly appear or disappear. And it's that removal. My favored view is it's the removal of the actual resources at the end of the lake, which is most important. The interesting thing is when you fill up the Rift Valley with the lake, you suddenly get forests growing everywhere, all up the Rift Valley. So actually, it's a really difficult place for a bipedal hominid to actually live. And so really, we then get shoved out, and it's only when the lake starts to shrink that it becomes a nice place to actually go along the shorelines. And actually, most of these species are found in lake, shoreline, and riverine deposits that actually trap them. So my feeling is it's that removal or stress of food that has that driving force that says how we're actually going to get that food sources. And quite a few of these do go extinct at the same time as these appear.
If Homo erectus evolved into us, could the acceleration of climate change and destruction of habitat cause chimpanzees or other apes to evolve into a subspecies?
Oh, dear. Chimpanzees. You've been watching Planet of the Apes, haven't you? I can tell. The problem is that the climate change that we're looking at, which is over the next 100 years, in evolutionary terms is actually quite a small period of time. One of the key things that I think is important with these periods of variability is you get hit a number of times. So you get a lake coming and going, a lake coming and going, and you're doing this 4 or 5 times in succession over about 100,000 years. Whereas I think that the climate change that we're going to experience over the next 100 years has already influenced lots of species. Some of them have gone extinct, some of them will have to change their pattern of behavior, but actually I think chimpanzees, as long as we protect them, will be fine.
You may find this a bit facetious, but I'm just wondering, you talk about 20% of the calories being needed for our brains. Instead of going for a walk every day, could I put my feet up and do a couple of super fiendish Sudokus?
No, because unfortunately, it's actually not a facetious question. The problem is idling your brain doing nothing when we think we're doing nothing, and actually saying doing Sudoku, actually the difference in calories is 0. Actually just having the brain. It's like having a really nice sports car, but you've got it constantly running. Okay? And occasionally you do rev it up, but actually the amount of energy difference between that and just running it all the time is very small. So that's a great question, but no, unfortunately, I do suggest that everybody goes for walks, and everybody does Sudoku.
Okay, yes, please.
How much is brain size a factor in the tool-making aspect of...
Oh, brilliant. Yes. Fantastic question. And I'm going to swear you all to secrecy. This is interesting because, of course, Homo habilis was named man the tool maker. Okay, and that's why habilis is his name, because stone tools were found with the skull. And the species is pushed back to about 2.4 million years because a bit of a jaw, which seems to be this species, and stone tools are found at 2.4. So this is the tool maker. Unfortunately, or fortunately, because I think this is the great thing about paleoanthropology, Richard Leakey and his group have found stone tools which are much older. So we're talking, and you're sworn to secrecy. If there's anybody from nature here, don't talk to them. 3.2 million years. So it means that our little ancestor here, who is about this height, was using stone tools. Because this is why I talk about the social brain. Using tools is actually not that clever. Chimpanzees do it. There are quite a few birds that do it. So the interesting thing is, if that stone tool use is passed on from generation to generation, now that is an interesting thing. But no, it means that we're pushing back stone tool use back to before Homo actually appeared, which I think is very exciting. It's a great question. But don't tell anybody the answer. There's one over
Anybody
there.
else? We've still got plenty of time for more questions, so don't hold back.
Oh, this is Cheltenham. Of course they're not going to hold back.
Absolutely.
I'm always intrigued how much you can tell from a few fossils. Could you give us an idea how many complete skulls or bits of jaw you reckon?
Right. Okay. The estimate is that anything prior to modern anatomical human, so before Homo sapien, we have about 250 bits of different bodies. And so that's vary from almost the complete skeleton of Lucy to bits of jawbone or the skull you saw right at the beginning. So it's about 250 bits. For skulls, actually, those points that I had on the graph is all we have, where we have enough of the skull to estimate the volume. And that's why there's some big gaps in the record. So we know the species appear, say, about 2.5 million years, but we have no way of estimating their brain size. So I would say that reduces it down to about 40 data points for skulls. So not a very good record. Sorry? How do you know they're typical? Oh, we don't. We don't, and this is why you have to be very careful when we say ancestor. Actually, there could be one that we've never found, which actually led to Homo erectus from chimpanzee. And so we know these are ancestors or lineages that are related to hominids, and we are related to them. But actually saying, well, this one led to this one that led to this one, doesn't work at all. You're absolutely right. Oh, sorry.
Hi, I was just wondering how much of a role genetics plays in the story of evolution, or at all. I don't know. In terms of using that as an analysis tool.
What do you mean by using genetics? Give me a bit more to work with.
I don't really know.
Do you mean analysis of ancient DNA?
Yeah, that kind of thing.
Or looking at genetic clocks, for instance? Or
The DNA stuff is incredible. At the moment, we are exploding our knowledge on that. And literally, this is the new frontier. Unfortunately, Richard and I are just now old hat. It's the geneticists that are taking off. Some of the stuff that they've done, looking at, say, Neanderthal DNA, and being able to sequence large chunks of it, to see similarities between Europeans, Africans, and Neanderthal, incredible changes. And that understanding of how recent some of our adaptations. So yes, we're Homo sapien. Yes, we can go back about 180,000 years as a species, but many of the features, blonde hair, light skin, and things like that, and lactose tolerance and things like that, are incredibly recent in less than, say, the last 15,000 years. So genetics are giving us lots and lots of information. And for me, that's where the new frontier is, unfortunately. So if you go and see Mark Thomas's talk, yes, he will tell you lots more exciting things. He's actually in conversation with Marcus Bridstock, which will be great fun. A comedian and Mark. It's going to be great fun.
But these types of materials, they go out of, if we're talking about analysing for ancient DNA, these unfortunately go out of the sort of window of what we currently understand as being the window in which DNA survives in the paleontological record. About 100,000 years is sort of thought as being the window. So, but never say never. There's some incredible things happening.
But the other thing that the geneticists are doing is they're using our own genome to actually look through to see where there are particular adaptations. The one thing which I found out, and I found amazing things. I just sat there for a whole week in Kenya going, really? Wow, write that down. Did you know that all of you still have an enzyme inside your stomach that means that you can eat insects? Okay? You can actually process, which again, the number of enzymes that come and go in a population are huge, but actually almost every single human being on this planet can eat insects and survive.
They're not so different from shrimps, though, are they?
Well, yes, that's true.
Gentleman at the front here.
Oh, sorry.
Yeah, we talk about the evolution of the size and the growth of the size of the brain, but do we know anything about the size of different components of the brain and how they might have been important? For example, was the visual cortex more important than the bit of the brain where you've got emotion and social interactivity?
No, it's the simple answer. People have tried with incredible three-dimensional CAT scans to actually look at the actual imprint of the brain inside the skull and try to estimate the sizes of the different parts. That is not as successful as you would like and really doesn't give you a handle on. The cheat is actually we look at the artifacts. So we look at what have our ancestors left behind. Do we have pottery? Do we have jewelry? Do we have symbolism? And again, that's when we start to build up this view of culture and when culture actually came in. So unfortunately, the brains don't really, or the skulls don't really give us enough information. Some people have tried to look for much smaller bones. And one thing that is interesting, which is unfortunately not quite culture, the teeth give us a lot of information. Chris Dean at UCL has looked at the teeth, and you can see growth lines in the teeth. And what he finds is this species is born, grows, adult. This species grows, adult. Don't know about that one. Homo erectus grows, plateau, and that's called teenage. Okay, pre-teens, okay? Yeah, we have about 4 or 5 years because evolution decided to torture us. And then the growth. And so there's an interesting growth plateau that occurred 1.5 million years ago as some adaptation to the environment. And so that's an interesting thing. Why would you want to have a growth plateau? Is that because you need an extra 4 years of moody teenagers to actually imprint them with some knowledge of how to survive in the African plains. And so there's lots of interesting ideas. So that gives us an idea of how the brain's developing, but actually, unfortunately, inside is not that much information.
Lady towards the back of the front row, her hand up.
Whereabouts do you think you're most likely to find more very, very ancient skulls? You know, what are the most promising sites? Caves or desert? You know.
Right. That's the question that all paleoanthropologists don't talk about and won't tell anybody. It's like, shh, it's over here. I have to say, for me, the most important site for all of this is Turkana. And the interesting thing about Lake Turkana, and this is why Richard Leakey set up his institute there, was that it has a geological record going back to 65 million years ago. And so it's interesting that you can actually trace lots of changes all the way through. And this is where those new stone tools that you haven't heard about have been found at 3.2 million years ago. And actually, for me, that's where we're going to find a lot more exciting skulls if we're going to find them. But it's an incredibly labor and time-consuming pastime, and it's also a bit of luck. There are some people that just have that vision that can see a piece of bone in the dust just sticking out, and it's that and a bit of luck. So, but for me, Turkana, and with Richard Leakey actually trying to build that institute there and using it as a base to try and protect that area, that's fantastic. So that would be my answer, is Turkana.
Is there so to say a bit more about what type of deposit,
What type of deposit?
These sorts of human remains are found in?
Most of them are found in what were soft lake deposits riverine deposits, and cave deposits. So one of the most surprising things in the last 10 years was finding Homo florensis over in Indonesia, which basically was about this size, but actually had the body of this one, which is quite odd, and being only 15,000 years. So there seems to be a remnant, a pygmy remnant of Homo erectus somewhere in Indonesia, and we found them in cave deposits. And so they had been going into the cave, dying, and actually then building up in the sediment. But the African ones are mainly in lake and river silts, which then have solidified.
Okay, I think we. Oh, one more question. Go on. One or two more questions. We can.
You missed him. Oh,
gentleman over here. Sorry, with the dark top on.
See, you shouldn't have gone for the last one. He's going to ask a really mean question now, I can tell.
I was just wondering, can you tell if they can swim? There's
Sorry?
lots of lakes around. Were they swimmers?
If you're going to talk about the aquatic ape theory, we're going to have a talk later. No idea. Absolutely no idea. There is no reason why Homo erectus could not swim. I have no idea about the others. But you find that chimpanzees can actually wade. They don't do swimming very well, but they can wade through water, and you see them standing up like this, wading through lakes. So these would have been quite happy wading through lakes. And this one, the other thing I should have mentioned about Homo erectus, and Richard would tell me off for wasting time, but here, he also is running man. The interesting thing is Dan Lieberman in Harvard has done an analysis of Homo erectus, and there's lots of really exciting things, from your tendons to the way your neck works, all means that we can run. And all of you, if I trained you for a year, could run a marathon. It's quite interesting that actually it's something that's quite natural that humans can run a marathon, which is bizarre. And if you ever don't believe me, go out and you find that when you walk, your head does this. When you run, your head stays exactly level. Because of all the way your shoulders and everything is fixed, your head stays exactly like that when you're running. Just so you can make sure you find that prey.
There was one more question, the lady just in front of the pillar there.
You've mentioned lactose tolerance a couple of times. Presumably, as they were mammals, they were all lactotolerant when they were born. Is it something that they lost, and having lost it and we having got it, why have we got it? Why did we suddenly decide we wanted to go on drinking milk beyond infancy?
Do you want to answer that one?
Yeah, the question is really one of, it's not lactose tolerance, which we all are up until the time we're weaned from mother's milk. The question is the lactase persistence gene, which appears to have evolved once we started to consume ruminant milk. Then we had to, then in later life, have the gene available that we could still process the lactose, which would otherwise be toxic to us. So it's the question is us actually, which we all have the lactase digestive capacity, but it's actually whether that digestive capacity actually extends into later life, as it does in most of the people in this room, I guess.
And it must have had a very strong selection. So the interesting thing is that it's found, firstly, about 8,000 years ago in central Germany, and that seems to have then radiated out into bits of Africa and bits of Europe. Richard's just got a paper coming out in Nature, shows that milk was actually on pottery
area
in West Africa.
7,000.
But it's the key thing is that those that weren't lactose tolerant were the ones that actually died out. And therefore, there must have been a very strong drive to actually allow those that had that extra bit and were able to process milk through the bad years to actually survive when the others didn't. It's a little bit like the Scandinavians have an incredible sort of drive to have blonde hair and light skin, because, of course, they could actually absorb much more sunlight, allow them to actually produce vitamin A so they didn't get rickets. And so it's an incredibly strong selection. This is why all Scandinavians are incredibly fair-skinned, because anybody who didn't have fair skin got rickets and died. And this is unfortunately how evolution works. It's about sort of like the survival of those that have that extra little bit of edge. And this guy and you guys all have that edge. And that's something I do point out. I'm going to end with this, so Richard doesn't have to wrap up, is the one thing I will point out to you is all of you are incredible. Because all of you are survivors. Every one of you is from a lineage of brilliant survivors, all the way from the first bacteria, well done guys, all the way through, you survived the dinosaurs, you survived the extinction, you survived all of this, and your parents got it together and you survived that, and therefore all of you are incredible evolutionary survival stories. Well done.